The particle zoo. As the energy of colliding particles increased with improved particle accelerators, many new particles were discovered. It turns out that many particles which we thought to be fundamental are actually made up of more fundamental or basic parts. Many other particles were predicted by reason of conservation rules, and later were detected when more sophisticated technologies came to be. The Higgs boson, for example, was detected in just 2012 at CERN after 40 years of searching. Its elusiveness got it named the God particle. Elementary particles. An elementary particle is not made up of other particles and has no internal structure. An electron is an elementary particle. Protons and neutrons, however, are not elementary particles. Protons and neutrons are made of quarks, but a quark is an elementary particle. Quarks. There are 6 different quarks, and each quark has an antiquark. So here are their names. There's the up and down quark, the strange and charmed quark, and the bottom and top quark. And we use the symbols, that is their first initial, U for up, D for down, and so on. And they have a charge. If we take an electron to have a charge of 1, well, the up quark has a charge of plus 2/3, and the down has a charge of minus 1/3 of that of the electron. And you can see that all the quarks have fractional charges. And their antiquarks are named the anti-up, U with a bar over it, anti-down, D with a bar over it, etc. And you can see that the antiquarks have the opposite charge to their regular quarks. For a particle made of quarks to be stable, it must have a whole integer charge, so that would be +1 or -1 or 0. Okay, so these quarks, to make another particle, must be combined in such a way that their charges add up to +1, -1 or 0. So let's have a look at that. And we have 2 main ways of doing that. The first one creates particles called baryons, and baryons are made using 3 quarks. Okay, there's our table of quarks again. And the 2 main baryons that we're very familiar with are the proton and the neutron. So let's look at the bottom table, and let's take a proton. A proton is made of 2 up quarks and 1 down quark. That's UUD. And if we look at the combined charges of the 3 quarks, we have U plus U gives me 2/3 plus 2/3, and a D down, which is -1/3, and all together they combine to give 3/3 or +1. And we know that the proton has a charge of +1. Let's look at the neutron. A neutron is made of 1 up quark and 2 downs, and when we combine their charges, that's +2/3, -1/3, -1/3, and that gives an overall 0. And we know that the neutron is neutral. And can you see also that there is just a difference of 1 quark between a proton and a neutron? A sigma quark is mentioned there, that's 2 downs and strange. And when you combine their charges, you get an overall charge of -1. And there's many other baryons, and we'll see them in a table in a moment. But the 2 main baryons that we're very familiar with are the proton and the neutron, and they are made of 3 quarks each. mesons. Mesons are made using two quarks. So here's our tables again. And here are examples of just two mesons, and there are many different ones. Okay, so the pion is made of an up and a down quark. So when you combine their charges, 2/3 plus 1/3, we get an overall +1 charge. So again, for those to be stable particles, for the pion to be stable, it must have a whole integer charge, which it does, which is +1. And kaon is given here as another example. That's a down and a strange quark. That's +1/3, -1/3, and it has charge 0. Now in your formula and tables book, page 48, you'll find this page, and on the bottom half you'll see there listed mesons. So we just saw the pi and the kaon. You'll see their symbols, their masses, and their half-lives. So notice many of them have very short lives, so they're not really stable. Okay, versus we've got the baryons underneath. We'll see the proton and the neutron, the top two, and the proton is classed as stable, and the neutron has a relatively long half-life. And on page 49 of your formula and tables book, you'll find a list of the 6 quarks and each of their charges and their symbols. Before we move on to any other types of particles, we must talk about the fundamental forces of nature. So there are 4 fundamental forces, and they each have different ranges, different strengths, and apply to particles and objects of different properties. Okay, so we'll start with the strong nuclear force. It is very strong at very short range, and it acts on things like protons and neutrons, basically things in the nucleus of the atom. And its occurrence, or what it does, is it binds the nucleus, holds the nucleus together. And you can see that its range is really short, by 10 by -15 meters. Okay, so over really short range, or the size of the nucleus of the atom. Okay, that's the strong nuclear force. Then we have the electromagnetic force. We've met this in our electricity chapter. It has about 1/100th of the strength of the strong nuclear force, and it acts only on charged particles. Okay, what does it do? Well, it binds atoms and molecules together. Why does the electron orbit the nucleus? Because the negative of the electron is attracted to the positive of the proton, etc. Okay, and its range is infinite. Okay, yes, it does fall off with distance squared, but theoretically it's felt forever. Okay, it gets weaker and weaker, but it is there. Okay, that's electromagnetic. Then we have the weak nuclear, and you can see by the numbers there, it is tiny in comparison to the strong nuclear, extremely weak. It acts on all particles, and it's evident in beta decay, and has an even shorter range than the strong nuclear. Okay, finally we have gravitational force. Again, it has a very, very small relative strength. Okay, but it acts on all particles that have mass, so that's all particles, and it binds the universe, and it has an infinite range. So a particle on one side of the nucleus is gravitationally attracted to a particle on the other side of the universe, but in general it's so tiny we don't really notice it. Okay, so particle classification based on the forces is, well, we have one group called the leptons who do not feel the strong nuclear force. Okay, they're leptons. And another group called hadrons who do feel the strong nuclear force. So let's look at leptons first. Leptons are elementary particles. The electron is an example of a lepton. Other examples include, well, here's the table of them. Firstly, we have the electron of charge -1 and the electron neutrino, which we've seen in beta decay. So the electron has its matching neutrino. Then there's another elementary particle called the muon, similar to the electron but much bigger, less stable, also has a charge of -1, and its matching neutrino is also a lepton, the muon neutrino. And then there's the tau particle, much bigger than the electron, charge -1, very short life, and the tau also has a neutrino, the tau neutrino. So they are the lepton family, and they do not feel the strong force, the strong nuclear force. Hadrons then we've already met. They do feel the strong nuclear force, and they are the baryons, if you remember, made from 3 quarks, and examples of those are protons and neutrons, and the mesons made of 2 quarks each, and examples of those are the pion and the kaon. And a summary of all that is on this next diagram, and here we see our particle zoo. Okay, broken up into leptons and hadrons, and then the hadrons are broken into mesons and baryons.